So Josh Pepper, who is from NASA headquarters, is going to talk to us about the Outer Worlds Observatory.
All right. Thank you very much. Okay. Just want to make sure I know how this works. Okay. All right. Thank you all very, very much. I'm very pleased to be giving this talk. I am also here in lieu of someone else. I am the HWO Deputy Program Scientist. I'm here representing the whole mission, especially the lead program scientist, Megan Ansell, who had to be at an alternate event today. But I'm going to tell you about this project, which we're very excited about. So some of you might have heard of this, some of you might not. HWO is the next big astrophysics mission that we are planning after the Roman Space Telescope. HWO is defined primarily by the results of the ASTRO 2020 Decadal Review that determined that a large space-based infrared, visible, and UV space telescope was the primary, highest priority for space-based astrophysics for the coming decade. Its primary goal is to directly search for signs of life on planets orbiting nearby stars and to perform transformative astrophysics. And I'll tell you what those mean. So in order to understand this, it's really important to realize that we've been thinking a lot about how we do large missions at NASA. And we've got all of these formal reports that describe what we've learned from past efforts to do this through Hubble and Chandra and Spitzer and Webb and other projects like that. And so our goal is to co-develop the mission science, technology, and architecture earlier in the mission concept phase of this. So if you've been curious why it's 2025 and you haven't seen as much public progress on this mission as you might have expected, a lot of that is because we are working very, very hard to get everything planned much more thoroughly early on before we actually start cutting metal and even finalizing the initial designs of the mission. So HWO is going to be different in a lot of ways. We are designing it from the beginning with the intention of having in-space servicing possible. And this is for a mission that is going to L2. We are planning for the ability of robotic spacecraft to go out and do things like refuel or swap instruments at L2. We're building upon technology that we've already been developing for missions like Webb and Roman, especially the knowledge gained from developing the Roman coronagraph, which is a technology demonstrator in the Roman mission. We're going to be using next generation rockets. One of the reasons why projects like the James Webb Space Telescope were so complicated is because they had to fold up into rockets of a given size. And we're planning to make use of the next generation rockets that you might have heard of in order to take advantage of larger size and mass that is allowed by those rockets. And then I'll really point out the idea of maturing the technologies first. So the next several years is going to be developing the technologies, the detectors, the coronagraphs, the coatings that are required for this mission to be successful. The mission is led out of a project office at NASA Goddard, but with full participation from individuals at JPL as well as other NASA centers. You can see the individuals listed down here, including Lee Feinberg as the principal architect, and I'm part of the headquarters team over here who is helping, working to make this happen successfully. Okay. HWO, as I said, a space-based telescope with a nominal mirror diameter of something like 6 meters, but we are working on exactly what size is going to be necessary. The bandpass, it's ultraviolet, infrared, and ultraviolet, visible, and infrared, ranging from about 100 nanometers through about 2.5 microns. It'll have at least these 3 instruments. It'll have a coronagraph to achieve the goal of directly imaging the reflected light from an Earth-like exoplanet orbiting a nearby Sun-like star at a 1 AU orbit. It'll have a high-resolution imager, basically a wide-field imaging tool that will allow us to do incredible astrophysics of many different varieties that I just simply do not have time to get into in this conference. It'll also have a UV multi-object spectrograph or integral field spectrograph that will be also contributing to the science areas, and as well as potentially a fourth instrument yet to be defined that we're still figuring out. So this is a rendering of 3 different possible architectures for HWO. HWO will not look like any one of these. These are what we're calling exploratory analytic cases, which are engineering designs that we're using to help make sure that we're finding the pain points where we really have to push our technology hard in order to successfully develop this mission. So these are 3 different versions of what the architecture of the mission might look like, and then we're going to toss these out in the next year or 2 and develop the next generation of exploratory analytic cases to build upon the lessons learned from the theoretical analysis of this kind of work. But ultimately what we want to get to is this. This is a simulation of what our solar system would look like if observed with an HWO-like instrument from a star roughly 10 parsecs away. And we've got the coronagraph blocking out the light of the sun, and this pale blue dot here, that is the Earth, is what we are going to be breaking down into its constituent wavelengths to look for the spectral features of the sorts of things that we believe are indicative of a living biosphere on the surface of the planet. We want to be able to look for things like signs of ozone, molecular oxygen, water vapor, methane, carbon dioxide maybe. All of these are things that we collectively refer to under this broad category of biomarkers that are that will allow us to ask and then preliminarily answer the question, is there life on that planet? And as you can imagine, there is a huge amount of both degeneracy and false positives that we're worried about. And so there's a huge amount of work going on right now to decide how can you turn, how can you turn a set of individual spectroscopic data points like this into a degree of confidence that there is or is not life visible in the reflected atmospheric spectrum from that planet. But we're not just going to do this, of course, for one planet. We're going to do this for about 25 Earth-sized exoplanets in the habitable zones of these nearby sun-like stars. That number 25 is important. It's approximate because we're still working on precisely what are the design requirements, but the reason is if we find life on only a single exoplanet, that is not good enough for us. What we need to do is to find whether there is life confidently or there's confidently not life on enough exoplanets to decide whether there is a statistically robust claim that life is rare or common on these types of planets. That is the goal of this mission. Our intention is to determine, is life common or not in the universe? Now, it is absolutely true that that depends on our assumptions about our confidence in whether there is life based on our interpretation of these kinds of spectra. That is an incredibly hard thing to do. This is why we're working on this over the next decade and a half, because this is a mission that we are intending roughly to launch around the late 2030s, early 2040s. We can't be more specific than that because that depends on so many factors beyond what we know right now, but that is roughly in line with the amount of time it takes to finally launch a flagship scale mission after it has actually been selected as the top priority in a decadal survey. Now, because this is a conference about Know Thy Star, Know Thy Planet, it is obviously the case that we need to know the stars that we are targeting for their planets to an extremely high degree of precision and accuracy. At a very preliminary level, here we show that we want to know, when we observe these systems, what is the mass and radius of the planets that we're observing, what is the orbit of that planet, what are the properties of that star, the age, the spectrum, all of the kinds of properties that we've been talking about the last week. We want to know that. And so in order to do that, we want to ask this question, what do we need to know about the stars in order to enable this search for life? We have been working very, very hard on this. Our colleagues here in the Exoplanet Exploration Program, Eric Mamajek and Carl Stapelfeld, have put together a very preliminary list of potential target stars for this. Remember, these need to be fairly nearby main sequence, roughly late type stars that are amenable to the direct imaging needs of this mission. Other people have been further developing those lists of stars. I know Noah Tuco here has been working on that, as well as others. And we're starting off with these preliminary lists of stars and then narrowing down to a final set that will actually be observed. And the kinds of things we need to know are, what are the spectral types of the stars? We need to know what are their distances, their stellar brightnesses, what are the zodiacal light properties of those systems that would, allow or block our ability to image the planets. What are the other planets or stars that are in those systems that would potentially interfere? What are the properties of the star that would allow us to then infer the properties of the planet? If we don't know, say, the mass of the planet, then our interpretation of those spectra is going to be impaired, and so we need to be able to know, for instance, what the mass of the planet is, which requires often knowing the mass of the star. We are exploring possibilities of both using extreme precision radial velocity as well as astrometric techniques for measuring those planet masses. And we also need to know what are the properties of the stars or the planets or those systems that will inform our interpretation of these exoplanets. The bulk system properties, like the overall age of the system or the overall dynamics of the system, including all massive objects there, as well as what are the stellar properties that affect our ability to measure the planet properties, which, everything, I guess, is what we've been hearing over the past few days. So, we are now in a process of transitioning some of the work that we've been doing. You might have heard elsewhere, we are in the process of standing up a community science and instrument team. This is the CSIT. This is a group of about 20 community members. There is a Dear Colleague letter out now seeking self-nominations for this. So please think about whether you'd like to volunteer for or submit your name for this team. These are the activities. They're basically going to conduct scientific studies to support this mission, as well as input to the technology, with the activities to start in the middle of this year. And then the last thing I just want to note is we have a conference coming up. This is the HWO 25 conference. It is taking place this summer, July 28th to 31st in Washington, D.C. The abstract deadline for this has been pushed. It is now Friday, February 21st, so there's still time if you'd like to submit an abstract for a talk or a poster at that meeting. And I will leave this up because I'm sure there are some questions, and we are excited to see people there. Thank you all very much.
All right, so is there questions for Dr. Pepper? I love saying that.
It's okay.
Hello, Dr. Pepper. Very exciting talk.
Go for it.
I have a couple of questions about the coronagraph, and I guess I'll just ask the first one first. Is there any prospect for a multi-object coronagraph, like, say, for example, a type binary system or something else of that nature?
There are a number of different coronagraph designs being explored, including those that would permit the search for planets orbiting stars in visual binary systems. The nature of those coronagraphs is wide open, and those are exactly the kinds of technology design studies that are being conducted right now. So you don't really have a multi-object coronagraph. You have a coronagraph that will allow you to detect planets in a multi-star system of various types.
Got it. Okay. And can I stay on the mic for just one quick second?
Sure.
Is something like TRAPPIST a good target
No.
for... No?
No.
Because it's too cool?
Can't be done. It's the stars. The projected separation of the planets from the star is way too close
Gotcha.
for us to detect with direct imaging.
That's helpful framing. Thank you.
All right, other questions for Josh? Way in the back. Sorry. Sean, behind you.
Yeah, there's very few M dwarfs that we'll be able to target with this because the habitable zone of M dwarfs.
Sean.
Oh, sorry.
Because the habitable zones of M dwarfs are just too close to the star.
Hi, I'm Alejandro Suarez from the IAC. I wanted to continue on this. What's the expected projected separation you're aiming to?
I really should know this. I mean, basically, you want to know like in milli-arc seconds, or
Yeah, in arc seconds.
Great question. I don't have that off the top of my head.
Okay.
Yeah, it would actually depend on the. It would depend on certain properties of the system. Basically, how many lambda over d can you get, within there?
Just a ballpark estimate we had in our Memijex-Stapelfeld plot. It's something like 70 milli-arc seconds.
70
We'll
milli-arc.
get you ballpark 100 stars that'll get you close given certain values of Eta Earth. So something like 70, but that's there's wiggle room there.
Yeah.
All right. And if Eric, you have a really quick question in the back, if it's quick.
Eric Pettigura, UCLA. So you mentioned astrometry really briefly.
Yep.
Does that mean SIM is rising
What?
from the ashes, or?
I did
Is
not
that-
say that. I realize I'm here in Pasadena. No, I did not say, no. What I will say is we are exploring all options, including what is the ability of the HWO observations themselves to conduct sufficient relative astrometry between the star and the planet and any other objects in the system to conduct that measurement to the precision needed. Beyond that, we are interested, in fact, some of you might have heard there is a call out right now, although I think actually the deadline might have passed, called the EMPP, which is the Exoplanet Mass Measurement Program, which is soliciting science cases to explore further ways to develop both EPRV and astrometric techniques for better mass measurement precision for future generations of spacecraft, including for purposes of things like HWO.
All right, let's thank Josh and actually all the speakers.